Thank you. Hopefully the mic is on and everything. So first, a couple of questions. How many people, well, which of you know about availability zones and regions? Okay, there are a few that don't, so I will talk about an availability zone and a region as I'm going through because it's mentioned in a few of the slides. How many know about what DynamoDB is? Okay, small number. All right. Okay, so I will skip over. We'll see how we go. I've got far too many slides, I always do, and I talk too much all the time. So I will need kept to my time, and I apologize when I inevitably run over. Okay, so I'm a senior solutions architect with AWS, but I've only been on the vendor side for 3 years. I've been in customers for the majority of my career, so I've always been using this technology myself. And for the 2 jobs before AWS, I was using AWS extensively, which is what made me go, maybe I should work for them. I just seem to be sending money their way, so why not? And that's why I'm here. And DynamoDB is one of the services that just made me go, damn, that's cool. I really like DynamoDB. And it's something I've specialized in as part of AWS. So, giving you a little bit of the history, why NoSQL? We'll talk about the key concepts, have a little look under the hood. Can't go all the way under the hood, although it's amazing when you see how it all works. Managing throughput, feature highlights and takeaways. So, where did Amazon start with DynamoDB? Back in December 2004. Amazon.com was quite a large site, nothing like it is now, but quite a large site, and it was entirely built on Oracle as a database. And, you know, December, you can probably work out what's going on with an online shop in December. Lots of purchases going on, lots more people than expected. Database couldn't cope, and Amazon.com went down for several hours during peak traffic, which means lots of lost revenue, lots of annoyed customers, and potentially customers that don't come back for some considerable time, if ever. So the team behind the database side went, you know, every year we have this big peak and we spend lots of time trying to predict how big we're going to grow to during Christmas, and then we try and scale up our databases. And sometimes we get it right, sometimes we spend far too much money and we don't grow that much, and other times we get it completely wrong, and then it falls over. It's got to be a different way of doing this. So they spent a lot of time and looked at the database usage, looked into Oracle, which is a relational database for those of you that have not come across it yet, and it's an expensive proprietary relational database. I was a DBA for many years on Oracle. So yeah, I know it's very expensive and can be quite difficult to manage. And they realized in their traffic usage that only about 30% of the use of the database was relational. And the rest of it was just lookups. Lots and lots of lookups. And so they went, well, we've got to look at a different way of doing quick, fast lookups with predictable performance, and we need a different type of database. So 2007, the Dynamo paper was published, not the DynamoDB paper, the Dynamo, and that was looking at a different way of doing databases and a different way of scaling them, which we'll come on to. Initially, they came out with a database called SimpleDB, which is just about going out of use now. It's been around for a very long time. But in 2012, January 2012, DynamoDB was released for everybody to use. 2016, Gartner said things the usual way Gartner do. And then 2022, there's another paper which looking at DynamoDB and the way people are using it and the way it scales and the size it can scale to. What I really like about DynamoDB personally is it scales from absolutely nothing. So if you've got a personal project that you need a little database for, you can use it. It will cost you pretty much nothing. It should cost you nothing because of the free tier. And you can just use that. So when I first started mucking around with coding of my own projects, a SQL database or something that's going to sit on something in the cloud was going to cost me money. I don't like spending money. So DynamoDB was a really big draw because it could go down to absolutely nothing. And then it will scale all the way up to the level that Amazon is pushing it to. Amazon, a big customer of DynamoDB. Latest Prime Day was 146 million requests a second for a sustained period of time, which is quite a lot. And today it's a tier 0 service powering most of Amazon. What does that mean? That means that underneath a lot of the services in AWS is DynamoDB. So DynamoDB, very, very reliable. And if it wasn't, none of our stuff would be reliable because it is essential to a lot of our services. Okay. Now, the next 2 or 3 slides are going to make you think, oh, this has nothing to do with me. This is enormous scale. But this is just to give an idea of the sort of flexibility and scale that internet applications need. So we've got users all around the world. Quite often with these applications, we can't predict where they're going to be. So we need something as flexible and can span around about the world. We also potentially need massive scale, but when we first start off, we've got no idea what scale we're going to be. So we don't want to spend 100,000 building our own database, getting a proprietary database, putting it there, find we get no users, go, damn, that's a lot of money we've just burnt. I wish something had been free. Now, the cloud obviously makes a lot of this cheaper and less risky than it was when we were building data centers. But still, that risk is there. So data volumes can be anything from a few meg up to petabytes, exabytes, and beyond. Locality is global, and we need performance wherever it is. So we need microsecond type speed, and we can have millions of requests a second. But we could also go enormous peak, everybody's interested, and then nothing. So we want it to scale right down again so we don't pay lots of money when nobody's using it, and then have it scale up when people use it. Okay, so I'm going to move on from that. To give you an idea of what I've just said, let's say you had a sales drive and you put lots of adverts out there, which is going to attract users into your application. Your usage goes right up, and back in the old days you had to predict that and size your database and your servers and everything for that, and you really don't want to be doing that because you might get it wrong. As I say, this is showing big scale, but it works just the same regardless where you are in the scale. And I'll come on to what provision capacity is and all of that. Now, you probably won't believe this slide. Trust me. Well, okay, don't trust me. But this is basically showing a real graph from Amazon.com. And this is showing that as the amount of activity on the DynamoDB table was going up, and that's writes and reads. So that tiny little thing there says get item and put item, which are 2 of our APIs that we'll come on to. As the amount of traffic went up, the latency on the side there, this is milliseconds. The latency of the actions actually went down as the scale went up. And again, we'll come on to how that can happen. But yeah, that is a real world graph from quite a few years ago. Right, so one of the reasons for asking whether people know what a region is and an availability zone is for this slide and a couple of the other ones that were coming on. So a region is a collection of Amazon data centers, we'll call them. And they are located somewhere in the world in a geo region. So for example, we have the Dublin region, which is a set of data centers that are clustered around about Dublin-ish. And we can't say where they are. But if you're clever with Google Maps and a bit of searching, you can usually find them because they're pretty big. So we have users all around the world, and we really want our compute, our storage, our databases to be close to our users. So if we've got a lot of users down in South America and we're trying to serve them out of the UK, that's going to be slow, and they're not going to enjoy our application at that point, and they're probably going to go to a competitor who's got a faster, more responsive website. So with DynamoDB, we need to have the ability to replicate our data around the world, which we do with a feature called Global Tables. And unlike most relational databases, this is active-active. So you can write anywhere around the world into a DynamoDB table, and it will replicate it to all the other regions. And yeah, so there isn't a single active primary database or table. You can write to any of them and it will replicate to all the rest. Do shout out any questions if you have them as you're going along. Yep.
Let's say you write some data to one region, say in the US.
Yep.
And then at roughly the same time, you made a query for that data that was just added, say, in East Asia, for example. Would there be some brief moment in time where there would be an inconsistency in queries across the world? Or
yes, definitely. And we'll come on to eventual consistency versus strong consistency. You can get it within region as well. And that's kind of a penalty, if you like, for the massive scale and the flexibility and all of that. So yeah, it does come at a little bit of a cost of, you may query the data and it could have changed somewhere else, and you're getting a slightly out of date version. It's a small window, but if you're getting hammered with lots of queries, then it's going to happen. Yep. Okay, so performance at scale that we've talked about. Consistent single-digit millisecond is the thing that people always say about DynamoDB. That's for a single write or a single read. And it is consistent, very consistent. Nearly unlimited throughput and storage. We always write nearly because somebody could push it beyond what kit we've currently got in place, and then we have to rapidly put some more in. And Amazon.com is obviously doing that quite a bit. Massive scalability. And we have an SLA of 99.999, but it's up to. So the 5 nines comes with global tables. There is no maintenance window with DynamoDB. It is up and available all the time, performing at the same level. Serverless. I'm going to say something contentious and say true serverless. It scales to 0. So unlike some serverless things and some of our services as well, they call themselves serverless and then they say, and what size of instance do you want? It's like, hang on, that's not serverless. And if I don't use it, how much is it going to cost me? $100. Definitely not serverless. DynamoDB scales to 0 and can scale up from there without you having to change the way that you have built it or anything like that. 2 different types of payment classes, which we'll come on to. You can either pay per request, that is, you pay for each time somebody reads or writes something from your table, obviously in millions rather than, it's 1 penny or 1 cent per request. There's no provisioning, there's no capacity management, it's all handled for you. Okay, so key concepts, SQL and NoSQL. Now I usually put this up here and there's a whole bunch of people who know SQL and then they quiz me lots about NoSQL, but are there lots of people with SQL here? Or are you more likely to be NoSQL or neither? both, depends. Cool, okay. So SQL, I mean, originally, way back, just before I was born even, so I'm not that old. Well, I am, but SQL was created because storage, well, one of the reasons was because storage cost a fortune and compute was a bit cheaper. So it was designed to make data very, very efficient on the storage level, which it did through normalized and relational data. And it's very good at that, very, very good at that. And it's brilliant at ad hoc queries as well. So you can design something, throw it together, and then just start querying it. And then over time you go, well, that wasn't quite as efficient as it could have been. I'll just tweak my database and that's all fine. So scales vertically typically. Easily you can challenge me about that because there are databases out there like CockroachDB which can scale in a different way. But typically things like SQL Server and Oracle and Postgres and things like that, they scale vertically. And vertical scaling is where you replace one machine with a bigger machine and then put your database on it. So that's vertical scaling. Good for OLAP. So that's analytical workloads. And transactional to some level, but you then hit the sorts of problems that Amazon.com did as you scale. So NoSQL is optimized for compute. So this came out as storage costs went absolutely through the floor, and now the biggest cost really is compute and networking. So there was no need to optimize for storage anymore, and so we changed the way we deal with data. We denormalize it. What does denormalize mean? Well, it means that we might have the same data multiple times because we don't need to say, oh, that word Bradshaw, that's quite a lot of bytes. So in a relational database, we might have a table that says Bradshaw is record number 100. And then every time we want that name, we would go to that table and say, give me record 100. And it gives you Bradshaw. And that's much cheaper on the storage. Whereas in NoSQL, we'll just have, oh, we need that name. We'll put Bradshaw there. We need it there as well. Bradshaw, 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 Bradshaw. So we can end up with lots of different copies of the same data. But we can scale horizontally. So scaling horizontally means add another box. So we've got one box, well, 3 boxes running our database. We need more oomph. There's another one. We need more storage. Have another box. More. And it carries on scaling in that way. Brilliant for transactional processing at scale, at any scale. Any questions on that? Nope. Yep.
So saying that the denormalized database that you can risk ending up with a lot of like duplicate entries.
Yes.
Yeah, so in the case that you are trying to avoid that, it would be more down to the company or the user to try and avoid duplicate entries. So I mean, you need, I'd imagine, more, what's the word? Like planning. So you have to plan for that if you want to avoid these like risks of duplication, like such.
It might not be a risk of duplication. It depends exactly what you mean there. So a big disadvantage of NoSQL databases, certainly DynamoDB, is that you need to know how you're going to use the table before you create it. So you do planning up front with DynamoDB, and you think, right, I'm going to build this application. How am I going to access my data? I'm going to, read it in this way. I need to also be able to read it in this way. I'm going to update it in this way. And you do this planning first, design your table, create your table, and then it's fantastic. It's not great if you go, I don't know, I'll just throw it in there, see what happens. You get to a certain scale and go, that's not working. Right. I'm going to have to unload all of that. I'm going to have to redesign it, and then I'm going to have to build it again, put all the data back. Whereas with the relational, typically you can go, right, I got that design a bit wrong. I'll just tweak it as I'm going along. and I'll add an index here. I'll change the format of that table there. So yeah, that is a something that, well, to be honest, when you're dealing with DynamoDB with lots of customers like I do, that's typically where we spend our time, is what do we need to do so it will scale up to the level that they need. Okay, so scaling, as I've described while waving hands, traditional SQL, the database scales vertically, which means we increase the size of the server that it's running on. Then with NoSQL, we add lots of boxes, and we keep adding. Okay. Now, this is something that can trip people up when they first start using DynamoDB. You work with tables, you don't work with a database. So you basically create a table, and the table is your database. Okay? Now, what people with a relational background tend to do with, you know where this is going, don't you? Oh, okay. What people with a relational background tend to do is they say, okay, I need a table, right? I'll create a table. I put my data in it. Right. Well, in a relational world, I would now create another table, and I'd link those two together. So you create another table, and then you try and link them together, and you can't, because DynamoDB doesn't have a join, which is what you do in a relational database when you're joining two tables together. That's not how it works. So you typically work with one table for your data, and you can put different types of data in the same table, which you can't with the relational. With the relational, you basically lay out, let's say it's users, you would say, okay, that column is an identifier, that column is the first name, that column's the second name, that column is, their address, whatever it is. With DynamoDB and NoSQL databases, you go, right, I've got my primary key, I've got my sort key, and then, well, this item's going to be a person. So I'll add in attributes, which are the name, the address, all of that. Your next row could be something completely different with a completely different layout of attributes. There is no schema, not entirely true, but let's just say there is no schema. Every row could have different collections of data on it. Okay? Difficult to get your head around if you've got a relational head, but you can do that with NoSQL databases. And so you end up with, I should have put an example here of a typical, well, not a typical, but a table that I've built up myself, but you have lots of different types of data in there. So you will have, let's talk about, let's say a fitness database. You're doing something like Strava. You would have a table which has got all of your data in it. That table will have things like your profile. So it'll have an item in there for your name and all the details of your profile. It'll then have items in there for each of the exercise types you've done. It'll have other data like that. It might have data to an image or whatever. So all of that will be in the same table. And you don't link the tables together. But when you're working with tables, DynamoDB under the covers is splitting up those tables and distributing it over lots and lots of different nodes. Okay, and that's how we get the horizontal scalability. Now, for those of you that know DynamoDB, you'll probably know that each node can do 1,000 writes a second or 3,000 reads a second. And that's how we get our scaling. Add more nodes, get another 1,000 writes, another 3,000 reads for each node. You don't control how many nodes you've got, though. That's all automated for you. And what this scaling means is that as your workload changes, DynamoDB will increase or decrease terrible thing for me to have said. It will increase the number of nodes to match your profile. It never takes nodes away. It will stop charging you for them, but it never takes them away. And this is how you can get really big peaks completely handled without any sort of scaling going on in reality. So as you scale up, it adds lots of nodes so it can scale to that. As you scale down, it stops charging you because you're no longer getting the same write and read. But those nodes are still there, which means if you get a sudden peak, it can cope with huge throughput straight away. Yep.
Let's say you have a peak, and then a bunch of new nodes are added on, and you end up storing some data into those nodes.
Yep.
And then traffic subsides again. If you query new information, and it requires information which is contained in those new nodes that was created, would you be charged for the full scaling or just for the amount of usage?
You get charged for the amount of usage. So it's the number of reads or writes, and you get charged for the amount of storage that's being used.
All right.
And that's it. So it doesn't matter where it is. Yeah.
All right, thanks.
Okay, so a table made up of items and different attributes. So the A's are attributes. And as I was mentioning, with it not being a schema, those attributes can be names, addresses, all sorts, and each item can have different ones. And it's up to your application how you handle this. So you could say, if the partition key, this is in your application, if the partition key is, user, basically username hash something is the sort of construct we use, then it's going to be a username. And therefore, my application then expects A3 is going to be the name, the first name, A4 is going to be the second name, A5 might be their phone number, something like that. If the partition key is something else, like going back to the fitness idea, if the partition key is workout hash something, then the attributes will be something different. It'll be type of sport, how long you did it for, things like that. So each item can be a different, it can have a different set of attributes. Yep.
On the client side with their code, is there some way to have sort of static typing and sort of explain the schema, like here's what a user looks like, here's what a transaction looks like, so that you then have sort of static typing in your code, or do you have to just parse it as like JSON or whatever?
You choose, it's your application.
Right.
So you design how you're going to access the table, and then you access it in that way. I mean, you could just say, I'm going to treat it like a relational database, and the partition key is going to be a sequential number that's going up, and then I will only ever have this set of attributes. Not a very efficient way. You'd probably be better using a relational database, but you can do that. That's your choice how you make use of the table. Okay, and the sort key makes sure that similar data gets stored. It sorts the data as it's being written, and it means that similar data is stored together. What time are we on? Okay, I am going far too slowly as expected. So the partition key is mandatory. You have to have the partition key, otherwise you can't query, you can't write, etc. Optional is the sort key. It does help an awful lot with the sort key. It means that you can do much more clever things with a single table. Okay. Data types, pretty much as you would expect. So strings, numbers, binaries, etc. The one thing that people from a relational background usually say is, where's date? We don't have date. So normally we do that with string and put a Unix time in there, a Unix date even. Okay, so our very complicated, not at all, API The data operations, put, update, delete, batch write, and transactional write. It's a very, very simple API, and it stays the same API all the way through, regardless of your code. Your scale. Reading data, we query. We try not to scan, if at all possible. We do get item, which is give me this item from this table. Here you are. Batch get item, so give me lots of items. Transact get item is where I want to get items if other things are true. So scan, why is scan bad? You are charged based on number of reads, number of writes of a certain size. So your reads are, I'll simplify this. Let's just say writes are 1K, reads are 4K. Simplification, there are differences in this. So if you read something that is 400K, you will be charged 100 write units. Okay? So you try not to have big items like that. Anyway, scan reads the whole table, typically. So if you've got a big table, and you start at the beginning, and you've done a bad query, or you've designed your table badly, you will be charged for reading the entire table. Not a great thing. Has to happen sometimes. Ish. Okay. Thinking of time, there was one thing I wanted to really get to. I'm going to skip over global secondary indexes and the likes. Come talk to me afterwards if you are interested in indexes and things like that under the hood. Right, so item distribution. We've got all these nodes. We have to store our items onto these nodes. So we have a method of distributing them. So we have our partition key here, and it is going to hash based on partition key sort key, and it will then store it onto our partitions. Our partitions are effectively our nodes. Okay? So this never happens. This is perfect distribution across all the nodes. Amazing. Never really happens, that. That's a perfectly designed table. Okay, now, we've got all these nodes, and that would normally make a data center person go, well, that's an awful lot of storage that can fail. Don't like that. But what we do here in DynamoDB is we're writing 3 copies of your data in 3 different availability zones. Availability zone is part of a region. So an availability zone is it's a number of data centers. Each availability zone has its own resilient power, water, etc. It's separated from other availability zones. So an outage, if it affects one availability zone, won't affect another one. Availability zones are within a region. So let's say we're talking about Dublin. Dublin has 3 availability zones. Each of the availability zones are independent, so it's like having 3 different data centers if you're an on-premise person. You put something in one, you replicate it to another one, replicate it to the third. That's quite resilient. And that's what DynamoDB does automatically in the background. So it is writing copies of your data to all 3 availability zones across multiple nodes. So we have lots of nodes, potentially. How on earth do we deal with this? So we have 2 different types of nodes. We have the request routing nodes, and then we have the storage nodes. So the request routing node, this is a put item. So our user has done something to the application that's called a write. That put has gone to a request router, which has said, right, these 3 storage nodes are involved. Send the write to the leader node, and the leader node will then write it to itself. It will copy it to one other storage node, and then it will tell the application, we're done. And then, after that, it will write to the third node. And this is where eventual consistency and strong consistency comes in. Does that make sense? So request router, leader storage node, which then writes to the other two. Okay, so you would then say, oh, hang on, there's a leader. That then means there's a potential for problems with resilience, but every 1.5 seconds, these storage nodes are having a quick check on how each of them is feeling and whether they should change who the leader is. So if there's a problem with any of the nodes, 1.5 seconds, that'll change. Another one will take over, and failed nodes and things get replaced all the time, reboots, etc. So that is worked out nice and quickly. So consistency. Strongly consistent requests, which we can request in our code, will go to the leader node, because the leader node always has the most up-to-date version. So strongly consistent, which costs twice as much as an eventually consistent, always goes to the leader node. You get the most current version of data, and it only goes to the leader node. If you say eventually consistent, which is the default, it could go to any of the 3 of the nodes, which means there is a small chance that you'll get out-of-date data. Okay, so you design your application thinking of that as well. Or you go strongly consistent and pay a bit more. Okay, going to skip over indexing. All the admin is done, well, most of the admin is done for you. So create tables and indexes, that happens for you. You define what you want, it builds it for you. Splitting partitions, which is the next bit I'm going to... There's one bit I really want to get to, so I will scan forward, get to that bit. This presentation, by the way, is normally an hour and a half.
Oh, we use 7 minutes until 7:20.
Okay. So the admin's done for you. The one thing I want to talk about is splitting. So I will skip over on-demand capacity mode, provision capacity modes, and I want to get to this bit. Because the obvious thing in what I've said so far is, okay, there's lots of storage nodes, but what happens when one of these gets hot? So think of a catalog in an online shop. You don't control what's going to get hit regularly. So something suddenly becomes really popular because there's a TikTok that goes viral, something like that. And one item will go really, really hot because everybody wants to look at it, buy it, add comments to it, whatever. And if you've designed your table all nicely and everything, then you've got all this stuff spread beautifully across the storage nodes, but then you've got a hot item that's going to make everything else go a bit slower. So we've got adaptive capacity, which means that DynamoDB is constantly looking at what's happening to your table, what requests are being made to it, and it will take action based on it. So we've got 2 items that are, for whatever reason, might be a sales promotion, might be something viral, have become very busy. And DynamoDB will recognize this and go, right, I need to move them to separate nodes. So it will split that in the background. You can't tell it's happening. And it is split it onto 2 different partitions, which are different nodes. Now, if something has gone truly viral, DynamoDB will do that. It will take a single item and put it on its own storage node so that it gets as much throughput as is possible. Now, typically, when you're designing your application, you'd have caching and all sorts in front of this, so that you don't really want every single read to go straight down to the table, but initially, that's what it's going to be doing for you in the background. And it never collapses these back in again. If item foo here stops being really warm or hot, what DynamoDB will do is say, oh, there's capacity there. I'll start adding other items into that storage node so that you're not being inefficient in your storage. If it becomes hot again, it'll do the same thing. It'll split it off, get the throughput that you need, and everything is good.